Number 5. We have our alternating mechanism. And we have b to the n here. So if we take a look at b to the n, 2n over 4n squared plus 1. Remember, b to the n is positive for all n. And what we can see is the denominator is getting bigger faster than the numerator. So this is going to suggest that bn is decreasing. So 2n over 4n squared plus 1 and as you guys can see in Desmos, that's sure enough exactly what's happening here. So we got a decreasing series. All right, good. Now, as we look at the limit of bn, which is the limit of 2n over 4n squared plus 1, we divide by every term by n squared. Using, again, the calculus 1 approach, which gives us 2 over n, 4 plus 1 over n squared. We're going to look at the limit as it goes to 0. The numerator, or we should say, by properties of limits, this will go to 0, this will go to 0, so we really have 0 over 4 plus 0, which will be 0. Okay, so the limit here equals 0, and that means we satisfy the assumption that bn is positive, bn is decreasing, the limit is 0, so we have convergence here by the alternating series test. So we have convergence. All right. Number 6. We got the alternating mechanism. This is bn. So bn will be the square root of n over 1 plus 2 square root of n. All right. So what we can see is the terms are in fact positive for all n. And again, the numerator looks to be increasing faster. Sorry, the denominator is increasing faster than the numerator. So the terms are decreasing. So if you want to check Desmos, we have an issue here. Does not look like that is actually happening. Okay, we got a problem here. The n terms are in fact increasing. So this does not satisfy the assumptions that we need. We actually can't apply the alternating series test in this case. So then you say, well, what do we do with this if we can't apply the alternating series test? It doesn't apply. I'm going to say, consider the divergence test. So in that case, this whole series here we're going to look at as AN. And we need to consider the absolute value of AN. So the absolute value of AN is the absolute value of -1 to the n square root of n over 1 plus 2 square root of n. All right. So we're going to use some algebra here with absolute values. Absolute value of a product is product of absolute values. This is 1. All the terms inside are positive because n is natural numbers. So what we're seeing here is simply that the absolute value of AN is the square root of n over 1 plus 2 square root of n. Okay, so as you apply the limit to the absolute value, that's the limit of square root of n over 1 plus 2 square root of n. You're going to take now that square root of n, divide every term by the square root of n. Okay, just like you did in calculus, 1. So you get the limit now of 1 over the square root of n plus 2. N goes to infinity. This will go to 0, which means your limit actually goes to 1 over 0 plus 2, which is 1/2. That limit is not 0. So if the limit is not 0, then that means by the divergence test, this series diverges. So we have a divergent series here. So we can say equals 0. It diverges by the test for divergence. Okay, there we go. Number 7 here. You got the alternating mechanism. We got our Bn. Okay. Bn is e to the 1 over n over n. Bn is positive for all n. And Bn, let's see if this is increasing or decreasing now. So that kind of makes sense that we have a decreasing series. So Bn is decreasing. You can probably use calculus and show that the first derivative is negative over the interval from 1 to infinity. Okay, we just looked at the graph. Now, let's look at the limit of Bn and see where this goes to. Now, what do we know? As n goes to infinity, 1 over n goes to 0. E to 1 over n goes to e to the 0, which equals 1. So your numerator is going to 1, while your denominator is going to infinity. So that means our limit, because remember, n is getting big, it's the same n, 1 over something getting big is 0. That's the limit value. This is approaching 0. So this equals 0, and it satisfies the alternating series test conditions. Therefore, this series converges less than infinity. Converges by the alternating series test. Okay. Alternating mechanism, b to the n. B to the n is natural log n over n. And yeah, it looks like these terms are going to be positive. So you can say Bn is greater than 0 for all n. But the natural log, which one's increasing faster, the natural log or n? I think n is increasing faster than the natural log. But if we take a look at this, yeah, we start to see how this series really behaves. And I'm going to say you're increasing at 1. At 1, it's 0. And then at 2, it's larger. Starting at 3. So at 3, we will be decreasing here. Okay? You guys can see that there. Starting at 3. So really, what's happening with this series, you can say, well, 0, now n is 1. Well, this is when n is 1, we get 0. n is 2 now. We get negative 1. I take that back. Let me go back here. We're looking at this term here. So we really want to look at this starting at 3 to infinity. I think it's very easy just to kind of remark here that now for this series, it is positive, but b to the n is decreasing starting at 3. So from 3, n equals 3. Okay, and it turns out that's going to be good enough because we really don't care about the first two terms. They're finite, so an infinite value plus a finite will still be infinite, and finite plus finite is finite, so we're still okay. Just want to point that out to you. Now, the limit of Bn is going to be the limit of the natural log of n over n now. Okay, so n goes to infinity. That means we get infinity over infinity. So we're going to have to consider this as a function. If we look at the function now, natural log x over x, and we look at the limit now, as x goes to infinity, natural log x over x, we still get that indeterminate quotient here. So because it's an indeterminate quotient, IQ for indeterminate quotient, we're going to use L'Hopital's rule. And now that means we get the limit as x goes to infinity of 1 over x over 1, which really is the limit of 1 over x as x goes to infinity, and then we get 0 here. All right. So that means that this limit equals 0, and we satisfy the terms of the alternating series test. So that means we get convergence here, which means we get convergence here by the alternating series test. We're just taking a finite number, whatever that is, and adding or subtracting a few more finite numbers. So this series converges. Okay. Okay. So we actually have another alternating mechanism. And what that means is Bn is 1 over n factorial. Well, these terms are positive for all n, and they are decreasing because the numerator is constant and the denominator is getting bigger because n factorial, if you guys recall, by definition is n minus 1, n minus 2, down to 2 times 1. All right. So let's take the limit as n goes to infinity of b to the n, which is the limit, as n gets big, over 1 over n factorial. Now this is going to be 0 because the denominator is just getting bigger, bigger, and bigger. The numerator stays at 1. So this goes to 0. So it satisfies the terms of the alternating series test. So this thing converges by the alternating series test. We get convergence. Okay. Number 10, you have the alternating mechanism. Here's our Bn. Bn equals cosine pi over n. Okay. Well, I think we have an issue here, maybe. Cosine pi over n. Take a look at what's happening here. Well, let's take a look over here. Can't get out of there. Okay. So pi over n, let's take a look. Pi over x. So this is actually decreasing, but we want to know, what about cosine now? Just what I thought. Yeah, pi over n is decreasing, but cosine of pi over n, not necessarily the case. In fact, ladies and gentlemen, that first term is -1. Second term will be 0. Because you got cosine pi over 2, and then all the other terms are going to be increasing here. So what I want to remark is we cannot use the alternating series test because the assumptions that Bn are positive for all n, not necessarily true, but starting at 3, it will be true. So we know Bn is positive for n greater than or equal to 3. However, it's not decreasing. So Bn is actually increasing. So we cannot use the alternating series test. Take a look at this. Again, just to emphasize that. All right. 1, 2, 3. Yeah. Alrighty. So you might say, what do I do now that I can't use the alternating series test? I'm going to say, try the divergence test. I was going to write down test for divergence. So we're going to now look at this differently. We're going to look at it in terms of the absolute value now. Okay. So the absolute value is defined to be -1 to the n cosine pi over n. Now, using some algebra, absolute value -1 to the n, absolute value cosine pi over n. I think this is 1. And we got the absolute value of cosine pi over n here. We're going to look at the limit here. So let's think about this here. What do we know? As n goes to infinity, cosine pi over n goes to cosine of 0, because pi over n will go to 0. So let's write this in order. Cosine of 0 is 1. So this limit will go to the absolute value of 1, which is 1. Okay. This is not equal to 0. So by the divergence test, this series diverges. Now, we could have actually seen that from the beginning without going through the test for divergence. We could have taken a look at this and said, okay, well, we're going to leave it at that.